Good morning, and thank you for attending our technology session. We're excited to share our industry-leading knowledge with you. My name is Trent Tegg, VP of Sales and Development at Applied Fluid Power. As the world's largest fluid power distributor, we are here to help you take your machine and controls from concept to build faster and easier than ever before. If you'd like to learn more about electronics integration, technology, or the latest products and innovation, check out our blog, sign up for our newsletter, or visit Applied Fluid Power on LinkedIn. If you have any questions during the session, please feel free to ask using the question box on the webinar. We will do our best to answer them all. We will also be sending out a follow-up email offering a free one-on-one in case you have more in-depth questions. Thank you again for joining us. And now here's our presenter.
Hello, my name is Trent Kangas. I am an electronics integration engineer here at Applied Fluid Power. I have been with Applied Fluid Power for 6 years as an integration engineer, primarily integrating electronic controls into mobile hydraulic applications. For any typical mobile hydraulic application, I am tasked with specifying the electronic hardware, providing electrical drawings or documentation, and the programming of the electronic controls. In this presentation, we will cover details pertaining to mobile electronic controllers and things to consider when selecting a mobile controller. The agenda for this presentation consists of, first, what defines a mobile controller versus other smart hardware in the electronic control system, commonly used terms in reference of mobile controllers or industry terms for mobile controllers, the definitions and descriptions of the types of inputs and outputs that correspond to mobile controllers, the general hardware characteristics of mobile controllers, and things to consider when choosing an adequate controller for the application, such as I/O requirements, networking requirements, and software requirements. So what defines a mobile controller from other modules or devices in the electronic control system? There can be one or multiple mobile controllers within the electronic control system, or one controller with many slave devices or remote I/O modules, making it sometimes a little bit tougher to decipher between the two. The most common way to differentiate a mobile controller from other slave hardware is that a mobile controller typically has a custom programmed software application. This means that the code or logic application within the controller was created from a blank slate and was not just a device that had a couple of settings that needed to be configured. Typically, a mobile controller is also controlling some type of operation, such as receiving inputs and driving outputs that command valves, receiving CAN signals and commanding outputs, or commanding another device via network communication. This means that the controller will most likely have inputs or outputs and or networking, such as CAN, CAN bus, RS-232, Ethernet, etc. In general, the controller is usually what is referred to as the brains of the system, or the master device in the electronic control system. So, industry terms or commonly referenced terms for mobile controllers are things such as PLC. PLC is typically more of an industrial term for controller, even though the concept and sometimes the actual software are the exact same. Controller is obviously very generic, but can be referenced as such in a simple control system. Microcontroller is a term that Danfoss has given their line of controllers. By its role and characteristics, it is no different than any of the others on this list. Electronic control unit is just another example. A master device is a term used when a system may have other CAN devices that are strictly slave devices. Slave devices receive commands from the master, execute some type of operation, and may or may not respond with the result of the feedback. So master device is a commonly referred to term in a CAN open protocol of CAN bus. So on to controller I/O definitions. Aside from the vast difference in environmental ratings of mobile controllers versus industrial controllers, mobile controllers generally have physical inputs and outputs integrated into the hardware. In other words, they are not like the typical industrial PLC, where there is the CPU and the power supply as the main device, and then a number of slots where various types of cards or modules can be plugged in. With that being stated, it would be best to cover the definitions for the different types of I/O that can exist within a mobile controller. So starting with inputs, digital inputs are simply input signals that are either on or off, switched on or off, which could be 0 volts or floating to system voltage, which may be 12 or 24 volts DC. This could be devices such as push buttons, limit switches, operator inputs, etc. Frequency inputs are similar to that of digital inputs, sometimes can be configured as the same, but are capable of measuring the frequency of a signal. This being count the pulses, and when combined with another frequency input can determine the direction. These are typically proximity switches that are used for measuring the speed or frequency of something, such as like a wheel speed. Pulse counting can be used in parallel to frequency measurement for total distance or position control. And direction may be necessary for a bidirectional function, such as a ground drive. The graph at the right kind of shows a representation of rotation direction or direction reading. So like if input A, as you can see there, has a rising edge before input B, then it's obviously going in maybe what we'd refer to as the A direction. And if vice versa, where input B had a rising edge first before the input A, then we might consider it going in the B direction. So analog inputs are typically seen as a 4 to 20 milliamp current signal, various voltage signals, or as potentially a resistance. A 4 to 20 milliamp current analog inputs are most commonly used for transducers such as pressure transducers, temperature transducers, or maybe devices like inclinometers. 4 to 20 milliamp signals are less susceptible to noise because they are a current reading instead of a voltage reading, and in a system, electronic noise is picked up as a voltage. Analog inputs can vary in range. Example devices that would send an analog voltage signal are joysticks, angle sensors, foot pedals, transducers, etc. Most analog voltage signals are sent in the range of 0.5 volt to 4.5 volts DC, which allows for detecting whether the device is working or not. If the device is not powered on or is malfunctioning, the signal will most likely be 0 volts. Some analog voltage inputs can be configured as ratiometric. When configured as ratiometric, the PLC will most likely be supplying power to the input device, and if the power supply on the PLC fluctuates, it will compensate the fluctuation on the input reading as well. This allows for more precise readings on analog voltage inputs. Resistance inputs are most commonly used with devices such as a fuel level sender or temperature transducers. After measured from the input, the resistance measurement is compared to a lookup table, which relates a resistance value to a temperature or level. Moving along to outputs. Digital outputs are the simplest of outputs. They are an output that is either on or off, similar to that of a digital input. So when it's on or off, it could be 0 volts DC or system voltage, which could be 12 or 24 volts DC. There are two types of digital outputs. They can either be a high side, which is switching system voltage on and off, or a low side, which is switching between ground and an open circuit. Mobile controllers typically have digital outputs in the 2 amp and 4 amp range, or something similar to that. Some controllers can combine these outputs for higher amp loads, essentially running them in parallel and running a steady amperage out of each output. Analog voltage outputs are not common on every mobile controller. Analog voltage outputs are occasionally necessary for driving external devices, such as some servo valves require an analog voltage signal for control. There are also scenarios where a mobile controller needs to interface with some type of driver card or module that receives an analog voltage signal. So PWM outputs, or pulse width modulation, are very common among mobile controllers, as most hydraulic applications have some type of proportional valve. PWM outputs can be controlled via the traditional PWM control or current control, although not all PWM outputs, depending on the type of controller, are capable of current control. PWM control, or pulse width modulation, is the process of turning the switch between the supply and the load on and off at a fast rate. In return, the average voltage value applied to the load can be varied. The amount of time the output is switched on versus off is the duty cycle, as you can see in the diagram below. A 50% duty cycle would represent the same amount of time on as it would off, where a 75% duty cycle would be 75% the time on versus 25% the time off. So at 100% duty cycle, the output will send either the maximum current or the maximum current that the load will accept. In addition to the duty cycle, the output is also controlled at a specified frequency, or PWM frequency. Most valves and coils have a specific PWM frequency at which they need to be operated. And usually this is tunable within the software of the controller. Current control of a PWM output is simply executing closed loop control of a PWM output with current, in most cases milliamps, as the control parameter. This is also done within the controller internally. A PWM output must have current feedback on the output in order to provide current control as a control method. As the diagram below shows, the output is commanded with a desired current, which is received by the PID controller internal to the controller. The PID controller then applies a calculated PWM duty cycle percent to the output, then measures the current on the output and repeats the process. Most proportional hydraulic valve coils have a minimum current at which the spool begins to shift and a maximum current at which the spool is full open. Knowing these values, current control is more commonly used with proportional hydraulic valves, as it allows for more accurate control. Mobile controllers typically have PWM outputs in the 2 amp and 4 amp current output range, or something similar in that ballpark. So onto the characteristics that generally apply to mobile controllers. Mobile controllers have a few characteristics that make them unique and can reduce the complexity of an electronic control system, such as the outputs on mobile controllers are internally protected from overloading. Of course, the output can still be overloaded, but the output will go into a fault state and turn off instead of burning out. Typically, outputs are short circuit protected to ground and positive power. This eliminates the need for a fuse between the output and the load of that output. The outputs have a hard current limit as well as a soft current limit. The hard current limit would be something that's fixed and is proprietary to that controller, where the soft current limit is something that can be set in the logic or the code of the application. The inputs on mobile controllers are also internally protected. Typically, inputs are short circuit protected to ground and positive power. Inputs are typically high impedance to protect them from overcurrent, and generally voltage protected in the range of negative 24 volts DC to positive 35. Most mobile controllers have at least one master output relay. This is something internal to a controller, and it can be programmable. It's essentially a programmable internal relay that needs to be enabled for outputs to work. Some controllers have multiple output relays for individual output groups, whereas some just have one master output control relay. These relays can be used as a soft e-stop or a software e-stop relay, disabling the output circuits in the event of something similar to an e-stop scenario. So some other characteristics with mobile controllers. Mobile controllers typically have sensor power supplies. Generally there is at least one sensor supply circuit, if not more. These can be voltage configurable or fixed sensor supply outputs. Essentially they are a mini power supply for sensors that maintain a regulated voltage output regardless of system voltage fluctuation. They're generally low current in the range of 250 milliamp supply. With mobile controllers having internally protected inputs and outputs, this also includes the ability to provide diagnostics for the inputs and outputs. The controller can provide active or historic faults similar to an industrial engine. Example output faults are things like overcurrent, over voltage, or even open circuit. This would be if the output would need to be commanded to detect this and requires current feedback on the output. Or there's also faults such as short to power or short to ground. Example input faults would be over range voltage or current, under range voltage or current, depending on whether it's an analog voltage signal or a 4 to 20 milliamp current signal. Open circuit, or short to ground, or short to power. Where I/O diagnostics come in handy are when the control system has like a HMI or a display screen, where you can have a diagnostic screen within that display for troubleshooting your I/O. It can simplify your field service time. So now, once we've explained all the I/O, all the characteristics of mobile controllers, now comes the time when you need to select a mobile controller. Before selecting a mobile controller, it is best to gather all requirements and documentation for the devices that will be interfacing with the mobile controller. I/O requirements and quantities are the common place to start. In addition to the quantity of inputs that will be necessary, it's good to be sure that to account for each type of input, whether that's analog, digital, frequency, etc. Another thing to note is not all digital inputs can be configured as analog inputs. Not all analog inputs accept voltage, current, and resistance, in that not all frequency inputs allow for pulse counting and direction reading. The same is true for outputs, and another thing to account for is the type of output, whether it's a proportional digital analog voltage in addition to the quantity. Check that the outputs are rated for the load, is in amperage. If the max load current is close to the max output rating, this could present overloading conditions with inrush current on the load. Consider in that scenario, it's best to maybe consider sizing the output up. An example of that would be, if you're looking at a 2 amp output and you're running at like 1.98 amps, you might want to move that up to a 4 amp output to avoid that scenario. Not all digital outputs are high side, some are also switch low side. So with all that, with once you kind of gathered all your documentation and your I/O requirements, typically there's a range. There are different categories or controller sizes. This slide displays a generalized sizing chart for mobile controllers. The I/O can vary slightly outside of these values, but this is a good ballpark. When initially choosing a controller based on the I/O needs, it's a good rule of thumb to have a couple extra inputs and outputs for unforeseen additional I/O. This will eliminate the need to upgrade the controller for additional inputs and outputs, in the future. So as you can see in the categories below, typically there's kind of like what we consider our small category, which is between 12 and 20 I/O. Then you move up to a medium, and sometimes the physical size of the unit is really unchanged, and that's somewhere in the range of 20 to 30 I/O. And then you move into a larger category of 30 to 50, and then you get into extra large, which are fairly big size controllers at 50 plus I/O. So when selecting a mobile controller, in continuation of the I/O requirements, some mobile controller manufacturers have the ability to add expansion boards internally to the specific controller models. This can provide the ability to configure a controller with non-standard options or configuration, such as additional serial communication networks, additional I/O, whether that's just digital inputs, just analog inputs, a combination of, etc. As you can see on the slide there's some that have serial CAN. On the CAN there could be 4 additional CAN networks. Special PVG driver boards for specific valves. There's definitely many variations. The other thing, so networking requirements is a good thing to consider also when selecting a mobile controller. You'll kind of want to determine what type of communication you're using. Most applications call for some type of serial communication with other devices in the control system, especially if the control system has an HMI or display. CAN, or controller area network, is the most common of serial communications when it comes to mobile hydraulics and mobile controllers. You'll want to think about the quantity of CAN networks, and in addition to the quantity, you'll want to think about the protocol. J1939, CAN open, generic CAN. J1939 is the most common CAN protocol for mobile hydraulic applications. It's used for engine communication. CAN open is more common in industrial applications, but still has a presence in mobile control systems. CAN open can be used for various CAN transducers, whether that's inclinometers, etc. Generic CAN, this would be raw CAN messages that do not follow a specific protocol, such as J1939 or CAN open. But they are used in mobile applications where maybe you have a proprietary CAN message that you don't really want to follow a specific protocol. For applications that call for more advanced sensors, such as vision sensors, there is a need for serial communications that can handle more data. This is where Ethernet and RS-232 come into play. Typically, Ethernet and RS-232 exist in industrial applications. They're also becoming more popular in the mobile world, with telematics becoming more and more relevant. telematics, and this allows for remote connectivity, remoting into and going online with a controller, or remotely flashing programs and program files faster. The other thing to consider is the programming environment offered with the controller may be something that needs to be considered if there's a preference. Industrial controller applications have called for the program or application to be written in traditional ladder logic for maintenance purposes. The mobile world generally does not have a preference, but there are many options available. The Codesys software that is used amongst various controllers offers a variety of language such as ladder logic, the traditional graphic programming environment, structured text, which is logic just written strictly with text, something they call continuous function chart, which is a graphical programming interface that lets you drop in functions and function blocks and connect the lines and variables to them, or sequential function chart, which is similar to continuous function chart, but essentially is a graphical programming interface that creates logic in its sequential order. Again, these things are more of a preference thing, but maybe something to consider depending on who the end user is or who may be programming the controller. In addition to the programming environment as the software itself, a given controller tends to have a specific software environment in which they are programmed and cannot be programmed with other environments. Some software environments are simpler and easier to use, but at the same time can limit the capabilities, where other software environments leave the possibilities wide open but may require experience or training to be efficient in. This is just simply something to consider depending on the experience or requirements and who is doing the programming. So transitioning from the programming environment and software into the programming interface and hardware, there are also options to be considered. Typical physical programming interfaces are CAN, which uses some type of CAN to USB adapter that would plug into your PC, Ethernet, or USB. Programming or program updates over a physical CAN interface can simplify things by just connecting to an already existing CAN network in the control system. However, CAN communication is slower than connecting to a controller via Ethernet or USB. The results are things like longer download times or slower update rate when online or viewing your code live on the controller. Depending on who and where the production programs will be downloaded, a service tool could be of great assistance as well. Examples of what a service tool provides are things like downloading a production boot application or programs without the full software and licenses. So this would be something that might be of use to someone at production end of line where they're not actually writing the program, and so they don't need the full software and the license and license fees that go with that. The other examples are viewing controller parameters and faults for service purposes, such as field service personnel, the ability to manipulate selected program variables. An example of this might be the end-of-line production personnel manipulating calibration parameters. So that pretty much wraps up defining mobile controllers, the characteristics of mobile controllers, and things to consider when selecting a mobile controller. Thank you for coming to our webinar today. I hope that we were able to answer all of your questions. We will send a follow-up email with an opportunity to schedule a free one-on-one consultation. We'd be happy to answer any further questions that you might have. Don't forget to check out our blog and LinkedIn page for additional topics and to learn more about Applied Fluid Power's electronic control capabilities.